now, we're going to deal with the Laplace transformation of e raised to negative at sine bt. So again, before we start in this problem, since this is the last problem that we're going to solve in our Laplace transformation table, what I need to say that I forgot from our first problem that we solved is that how can I get, or where did I get my general expression? But it's still changing based on the given exponents and functions of the given Laplace transformation problem. Our general equation that we use every time that we express our first step is the integration from 0 to infinity of e raised to negative s x f of x dx. This general equation was always used every time in our first step, although sometimes the f and x are changing based on the given exponents of our problem. So, let's start. Our second process after we used our general expression is to find the integration by parts, or applying the integration by parts. So we got u, du, v, and dv. Then apply uv minus the integration of v du. So for u, we got sine bt. For du, which is its derivative, v cosine bt. And v is equal to 1 over negative s plus a e raised to negative s minus a d cosine bt dt. dv is equal to e raised to negative s minus a t dt. So, applying or performing our general rule for the integration by parts, which is u minus the integration of v du, we got 0 plus v over s plus a. Then finding its limit, we got 0 again over s plus a. Now, this will be our v du, such as the integration of 0 to infinity e raised to negative s minus a times t. So, after we get our first integration by parts and find this equation, then we're able to perform our integration by parts again. So we have to find our u du and v dv. For our u, we got cosine bt, and the derivative of our cosine bt, which are du, we got negative b sine bt dt. For v, we got negative 1 over s plus a times e raised to negative s minus a times t. And our dv is equal to e raised to negative s minus a t dt. So again, perform uv minus integration of v du. So since this is 0, and from the first integration by parts, the thing that we've left here is b over s plus a. Then we're going to distribute b over s plus a in the second integration by parts. So for the second integration by parts, we got negative cosine b over s plus a bt, e raised to negative s minus t times d. Then get its limit. As we go for infinity, approaches to infinity, we got 0. And as we approaches to 0, we got 1. Minus b over s plus a negative, and integration of 0 to infinity e raised to negative s minus a times d sine bt dt for our integration v du. Now, let's assume that our Laplace transformation e raised to negative a sine bt will be equal to y, or the given problem, which is equal to y. We got b over s plus a times the limit that we got here, which is 0 plus 1 over s plus a minus b squared over s plus a squared times y. Then transposing it to the other side of our equation, we got y plus b squared over s plus a squared times y is equal to b over y plus a squared. So again, we got y times s plus a squared plus b squared over s plus a squared is equal to b over s plus a squared. So again, applying some cancellation process or cancellation method, such as b over s plus a squared over s plus a squared plus b squared over s plus a squared, we can cancel same terms, of course, which is same denominator. Then we completely find that the Laplace transformation of e raised to a negative t sine bt is equal to b over s plus a squared plus b squared. This is how we get this problem.